Hello everyone, it's my honor to be here to have a presentation. My topic is Origami-inspired rigid and chiral model robotic arm. My presentation is divided into 4 parts: background, robotic arm design, experiments, summary, and prospect. First of all, the background. Nowadays, we still lack the support of robotic arms in confined space scenarios. We need a robotic arm that has the capability in constrained environments with high stiffness and dexterity. However, the existing related robotic arms are trade-off between large workspace and high stiffness. To solve these problems, we seek help from those rigid and chiral origami units. Based on the single unit spherical fallback mechanism, we extended it into a basic combination unit consisting of a series connection of a spherical fallback mechanism and a planar fallback mechanism. Furthermore, we can proceed with unit expansion, transforming it into a unit consisting of 2 single units, which maintain 1 degree of freedom and a large fold ratio. Meanwhile, we solved the thinking problem of the basic combination unit by using the method of offsetting the axis and plate. We chose a unit consisting of 2 single units as our arm section configurations in joint. Based on 3 different ways of combination, we can figure out the different outputs related to the same input. The arrow above refers to the output and the arrow below refers to the input. We have summarized the relationships of rotation and displacement so that different combinations can be selected according to specific needs. Now, it is also hard to design the real motor input and output on the input plane and output plane. To solve the problem and to make the joint module have better motion performance, we have designed the input according to the combination unit, allowing it to rotate and expand. Meanwhile, to ensure decomposing output, we optimized the planar fallback mechanism using a planar 5-bar gear mechanism, creating a new platform identical to the original one, enabling decomposed output within adjacent joint modules. So, for the RR joint, it has double extension size with 30 degrees deflection on counterclockwise. For LL, it has the deflection size with 30 degrees on clockwise, and LR is 0. And we can use different combinations to build the 10 DOF robotic arm with 4 joint modules, 1 rotational base, and 1 rotational gripper. Here is a workspace of our robotic arm. Based on the extension of different joints, the workspace is great and varying. And obviously, the fully extended state is twice longer than the fully folded one. Here are our experiments. On the right, you can see its amazing extension, grabbing the bottle beyond where it could reach originally. Combining origami, we have developed a rigid robotic arm that can adapt to work in confined spaces with flexible reconfigurations and adaptable workspace. In the future, it can be integrated into different robots to complete required works. Finally, here's a video about the robotic arm. This is how we made the joint module from a combination of units. Then you can see the display of the joint module. And the movement of our robotic arm. And you can see what it can do in the future. Thank you for listening.